Okay, hi everyone. I'm Nick. I'm from the University of Sussex, working with Charlotte on a project looking at the sustainability of computing, specifically in neuroimaging. And I thought I'd talk today about some of our empirical work and kind of present it as a case study for how you might use similar approaches in your own fields to try and measure the carbon footprint of digital pipelines. So this has partly been inspired by progress in other fields like machine learning, where there's already been a fair amount of work trying to measure and quantify and reduce the carbon footprint of computing. This has led to the development of carbon tracking tools, but also recommendations for how people can reduce the footprint of their own work, and predictions for how that will evolve in the future as technology changes. And I'll start with a bit of a case study from machine learning, which is a study I quite like. This is a study looking at crop pests and trying to classify pictures of them. So you could put in a picture and spit out what it was. As people know, these models often use a large amount of data, deep learning models, over a long period of time to train up classification accuracy. And obviously, the more computing you're doing here for this, the more energy you're using, the more carbon you're emitting. So if you can reduce the amount of data you're putting into these models, you can effectively, in the training, you can effectively reduce their footprint. What the researchers found here was that over 3 different levels of depth of their model, they could take out anywhere between 25 or 60% of the data and still have the exact same level of accuracy in training classification of these pictures, around 95%. Just showing that it is possible in cases like this to find a trade-off between how well your pipeline's doing or your model and its footprint. And we try to use a kind of a similar approach here in our work. So Luik's already covered these in quite some detail, so I won't go into them too much, but you have various different families of carbon trackers, including online calculators like green algorithms, embedded packages like Code Carbon and Carbon Tracker, and server-type tools like green algorithms for HPC, and tools like this make it easy to quantify the footprint of computing. Luik's also talked about his recent paper weighing up the different benefits and downsides of these tools, and I do recommend checking that out if you're considering using these in your own work. We recently released a preprint focusing on 10 recommendations specifically for neuroimagers to reduce the carbon footprint of their computing. And this covered steps throughout the research process, including study design, and then like the time and the location in which computing is run, thinking about the computing you actually need to do, where files should be stored and for how long afterwards, and how much you publicly share after the fact. And today I'm going to focus on recommendation 4 here, which is only running the data pre-processing and analysis steps that you need for your research purposes. And this is important because in human neuroimaging, as some of you will know, there's a huge number of pre-processing steps you need to run your data through to get it from from a kind of a raw, unprocessed format to a nice-looking one that you can use in analysis. And this includes steps like registration, so getting everyone's data into the same space, distortion correction, smoothing, so averaging out noise from the signal. All of this can add up, and in some cases takes more than 24 hours to run for a given subject. So there is in some studies a relatively high amount of compute needed, and therefore potentially a high carbon footprint as well. We chose to focus specifically on one tool, fMRI Prep. And for anyone who haven't heard of it, this is a tool that's it combines best practice options from a number of different packages, including FSL and AFNI, for instance, to produce optimally pre-processed fMRI data. And we like this pipeline because it provides this very variable command line structure. So you can sub in or out different pre-processing options, or you can vary them parametrically to affect the output of your pre-processing. We also liked it because it's recently had one of those embedded packages, Code Carbon, built directly into the command line. So just by toggling on this track carbon option, you can spit out estimates of carbon emissions for each subject's pre-processing. So this allowed us to look systematically at the effects of different pre-processing steps on emissions and kind of compare that across different variants of the pipeline. So for this, we had existing data, open access data from 257 subjects who'd completed stop signal task, which is basically either pressing a button response in response to a cue or stopping themselves from pressing a button. And we ran this same data through 10 different versions of fMRI Prep. So this included a baseline model with default settings in fMRI Prep. We had one where we removed this default step of free surface reconstruction, which is just there in the vanilla version. We did things like increasing and decreasing the amount of parallelization of the job, so diverting resources to it or giving it more resources. and adding steps like the correction of motion artifacts or distortion correction. So we ran out the same data through 10 different versions and looked at the carbon emissions coming out of each of them. I'll just stop for a little caveat here because, as I said, we'd intended to use this code carbon package integrated with fMRI Prep to estimate its footprint. This was by far the easiest option we could use, given that it was already there and up and running. We noticed this weird pattern when we were submitting jobs to our high-performance cluster, where we'd suddenly have these big bulges, basically, where things would be relatively flat, and then suddenly you'd have these really high estimates of emissions, depending on when the job had been sent to the cluster, which didn't really make any sense for us because these jobs should be running with their own computational resources in their own little space. They shouldn't be interfering with each other, or other things shouldn't be interfering with them. So using the exact same jobs, we ran a server-side tool similar to Green Algorithms for HPC on the same data. And what we found here was first that for these same jobs, the estimated emissions were about 10-fold lower. And also that these systematic increases and decreases in emissions over time had disappeared. What we found out after digging into the code a bit was that code carbon appeared to be estimating the footprint of everything that was happening on a given node that a job was happening on, which could include other subjects in fMRI Prep. It could include particle simulations from physics researchers, a bunch of irrelevant stuff basically that was driving up these estimates. So the server-side tool for our purposes seemed better at isolating the footprint of a specific task, which is what we needed here. I say this just because you may find that there's trade-offs between these different tools in your own systems in the future, so it's worth checking if you are using these systematically that they're doing what you'd expect them to do in a sensible way. But back to the study. So as well as understanding the footprint of our pre-processing, it was important to make sure we're doing a good job of pre-processing the data as well. Just like that case study at the start was looking at classification accuracy for pictures, we needed a way of knowing whether we were doing a good job, basically. So we did a bit of researching of the literature and eventually landed on a method of looking at the height of statistical activation in regions of interest, so regions that we'd expect to be particularly active for pressing a button, like the primary motor cortex, and for inhibiting a button response, like the pre-supplementary motor area. This is a relatively established task with predictable patterns of activation, so the idea was that a good version of this pipeline should produce higher evidence of statistical activation here because it's more sensitive to these effects we'd expect to see. This isn't a perfect method for measuring performance. We can talk more about that later, but it's the one used in the original validation of fMRI Prep and one that we thought was suitable here. So for each of our 10 pipelines, we weighed up the emissions in this dotted green line against that evidence of statistical activation in purple and pink here in solid. We've got baseline here in the middle, P0 with the dotted line, and our other experimental pipelines to the side of it. I'll say first that the average emissions for a given subject's pre-processing was around 0.02 kilograms of carbon equivalent emissions, which added up across the whole study, where we were effectively pre-processing 257 people 10 times, to about 40 kilograms of carbon, which is the equivalent to driving about 100 miles in a petrol car. So honestly, not bad. That's me driving to my parents' house and back in a couple hours. So it's not a huge footprint in itself. We were using a relatively small amount of data, it's worth saying, in an area of low carbon intensity. But this has allowed us to benchmark how much energy it takes to pre-process 5 minutes of fMRI data, which is interesting. Comparing our different pipelines, we can see several patterns. So when comparing to baseline, for instance, we can see that toggling off this default free surface reconstruction, emissions decreased by about 46% with no loss at all in our pre-processing performance metric. So this is kind of there's not even really a trade-off here. If you don't need the files that are coming from FreeSurfer, this is a very easy way to minimize your carbon footprint without losing anything in your data quality. For P2, we implemented this sloppy testing mode, which basically is intended for testing whether a pipeline will run to completion. You kind of cut corners on the registration of the data. And here we found that, again, decreased emissions by about 45%, but as we'd expect, also decreased performance by some margin as well. So basically, in this scenario, this isn't one you'd want to use in normal pre-processing, but something you could use in the early stages where you're figuring out just if something will run to completion, basically. For P7, we introduced Aroma, which is the automatic removal of motion artifacts, and found that here we saw a significant increase in the performance of the pipeline, but no increase in carbon emissions, surprisingly, or in the duration of computing. So this seems like an option you can toggle on relatively guilt-free to possibly improve the the cleanness of your data without increasing your carbon footprint. Finally, in P9, we turned on this field map-free distortion correction technique, which is, I think, relatively experimental within fMRI prep. What we found here is it's increased emissions by around 16%, but also decreased performance as well at the same time. So at least in our case, kind of the worst of both worlds and an easy one to avoid. I'll say conversations around the use of this tool are still ongoing. Even as a few weeks ago, they're trying to figure out what's wrong with this tool exactly. So not a complete condemnation, but for us, an easy recommendation to avoid. These results together have allowed us to make 7 recommendations for how users of fMRI prep can reduce the footprint of their computing. So this includes the no-brainer. If you don't need free surface reconstruction, don't put it on because you can halve your footprint with no trade-off. If you're testing, use this sloppy flag. You can use low memory mode to decrease your emissions by about 5%, again without any trade-off in performance. And there are options like ICA aroma, which you can toggle on to gain kind of luxury options without increasing your emissions. I won't go over all of them in detail, but effectively this has allowed us, we're putting out a preprint soon that will include these recommendations and will hopefully be quite easy for people to implement in their own pipelines. While I'm talking about fMRI prep, I'll just a little side note on the amount of data it generates. So for our baseline pipeline, on average, fMRI prep was generating about 5.5 gigabytes of data. Some of these will be final output files that you use in subsequent analysis, like pre-processed functional data, and a bunch of it will be stuff in the working directory that you're never going to use again, or stuff in the final output directory that some people might use, but you don't have any personal use for. For us, going on and running statistical analysis in FSL, we found that only 4% of the files generated were of actual use to us in a statistical analysis, and the other 96 didn't have any use for us, basically. And in response, I've developed this open source tool, fMRI Prep Cleanup, which automatically identifies what those junk files are and removes them from your directory. As we talked about earlier today, you can reduce the amount of files that you're storing, you can reduce the need to back them up on servers and therefore the energy needed for that, and also delay the need to bring in new servers when existing ones fill up. It's also just easier to sift through if you've got rid of all of this unneeded stuff. So given this is a bit of a case study, we'll talk about some general lessons that we've learned here. So for a given digital tool like fMRI Prep, there appears to be some low-hanging fruit for drastically reducing emissions without losing much or losing anything in performance. Choosing the right carbon tracker can be complicated, as we've seen, and if you're running this systematically, I would recommend checking that it's doing what you're doing when you're running these carbon trackers. Quantifying performance can also be complicated. So we looked at height of statistical activation. There are probably some people who would disagree with that metric. There are other approaches you can use, but there's no gold standard for saying how well fMRI data has been pre-processed. So you kind of need to choose the best available option. And it's worth checking if best practice does exist in your own field. We've had some experience communicating this to people in our department at Sussex, and neuroimagers generally seem to understand this issue and to some extent to appreciate the importance of it and to be interested in it. So it is worth communicating this to audiences in your field that may not have come across this issue, just in case they're willing to make changes in their own work. We've had some conversations with our high-performance computing team at Sussex, who are relatively open to installing things like server-side carbon trackers and task schedulers into the cluster itself to allow users to use. I've heard mixed stories of other teams not being so amenable, but it's worth having these conversations as well, just in case this is something you can institute at kind of an institution-wide level relatively easily. And again, digital tools can produce a lot of unneeded data, as we've seen, so it's worth developing these tools to automatically clean up data or just manually cleaning up yourself if that's a small enough job to try and decrease your footprint of data storage. I'll just finish by saying thank you to collaborators, including co-organisers Charlotte, Gabby, Lewick and Lincoln, as well as others, Ragav, Nikhil, Chris, Reese and Neil. If you're a neuroimager who's interested in sustainability, I recommend checking out the OHBM Sustainability and Environmental Action Special Interest Group, or CSIG. We have a research pipeline subgroup that focuses specifically on these questions, so we'd love to have you join up if you're interested. And finally, if you're interested in open source green computing neuroimaging code, including fMRI Prep Cleanup, that's all on my GitHub repository at the moment. But that is me done. Thank you.